So we're going to look at combinations, which is basically n choose k. So if you ever heard anyone say n choose k, they're calling it combination. So you'll usually see it drawn like this, or sometimes if you're in a certain kind of class, they'll do like that, combination n choose k. But it all comes down to the question of like, if you have n objects, how many different ways can you arrange them into groups of size k? So a pretty typical example would be like, okay, so let's say I have A, B, C, and D, and I want to arrange it in groups of 2. So that would be like 4 choose 2, like that, right? So basically the idea is you can either say like AB, you can go AC, you can go AD, you can go BC, you can go BD, or CD. So that means there's 6. So 4 choose 2 is 6. Easy peasy, sort of, I guess. All right, so to make sure we've got some of this all set, this number up here is called the upper index, and the number down here is called the lower index. Okay, so n choose k, there you go. Now there's a couple of different ways that you can set this up. The kind of standard, so the kind of standard definition that I've always seen is that n choose k is given by n factorial over n minus k factorial times k factorial. Okay, so that's like your standard definition, all right, which kind of makes sense. Well, I don't know if it makes sense, but that's how it's defined. We can actually check it for our little example where we have 4 choose 2. 4 choose 2. There we go. Come on, girl. So we had 4 factorial over 4 minus 2 factorial over 2 factorial. So 4 factorial is 4, 3, 2, 1. And 2 factorial times 2 factorial. So that's 12 times 2 is 24 divided by 2 times 2. So that's going to be 6. Yay. So that we verified that it works for this specific example. Yay. Okay. So, however, some people kind of notice, like if I was going to do this for, 5, I don't know, let's make something slightly bigger. So like 6 choose 2. I don't know why I did that. So like 6 choose 2, we'd have 6 factorial over 6 minus 2 factorial times 2 factorial. So hold on, just bear with me. So this is 6 times 5 times, and for lack of a better way to do it, 4 factorial. And on the bottom we have 4 factorial times 2 factorial. So the 4's cancel out, and I end up with the 6 times 5 over 2 factorial. I'm going to leave it like that actually, because that brings us to an alternative definition, which is actually n times n minus 1 all the way down to n minus k plus 1 over k factorial. Okay, so the reason that we might like this second definition a little bit better is because technically, so this is kind of weird, this technically works for n less than 0, for n less than 0, as long, or even n not in the set of integers, whereas this only works whenever n is greater than or equal to 0. Well, 0 wouldn't really make sense. 0 factorial is 1, but it works. Actually, I'll say strictly greater than 0. So this only works for n strictly greater than 0, and n has to be in the set of integers. So these are two alternative definitions that kind of seem like they mean the same thing, but they kind of don't. Also, if you're doing concrete mathematics and the Knuth notification, the way that they write stuff up, they do that as a falling power n blah blah k, falling power k over k factorial, where this is just defined as this. So it's just a shorthand for that. So it's kind of weird because you can end up with these permutations and combinations for negative numbers. So let's look at how that would kind of show up. So again, our definition is that n choose k can be given by n times n minus 1 all the way down to n minus k plus 1 all over k times k, well, I'll just say k factorial, all over k factorial. So let's say I have something like -1 choose 3, and that's kind of weird because it doesn't really make sense. How can I have a group of -1 objects and arrange it in groups of size 3? But, you know, the joy of math is that I can make it do whatever I want as long as I follow the formula. So n is that -1. So it's going to be -1 times -2 all the way down to -1 minus k plus 1. And this turns out to be -3. So it's really just -1 times -2 times -3 on the top, like that. And then on the bottom, it's going to be 3 factorial. So that's 3 times 2 times 1. And so that means on the top, we've got, well, it's going to turn out to be -1. So I can take -1 objects and put them into groups of 3 -1 times. So again, that doesn't really make sense, but it's just one of those weird properties of n choose k that you probably don't get into unless you get into some more of the upper level discrete math stuff. You can also use non-integers, which also kind of opens up a lot of possibilities that we're not going to get too much into here. But again, the idea is I've got -1/2, -3/2, and I'm going to go all the way down to -1/2 minus 3 plus 1. And again, this is going to turn out just to be -5/2. So that actually ends right there. And again, over 3 factorial. So I have -1/2 times -3/2 times -5/2 all over 3 times 2, which, let's see, that's going to get me to -5/16. So there's -5/16 way that I can group -1/2 objects into groups of 3. It's weird. I don't know what to tell you, except that we have these things defined because they come up, and just wanted you to know that it exists. All right, some other fun properties to learn about permutations, or about combinations specifically, is hopefully it's pretty clear if I have n objects and how many ways can I make a group of n. There's only one way that I can do that. So n choose n is 1. 0 choose 0 is also 1. So as long as I'm choosing n objects, if these two numbers are the same, if the upper index and the lower index are the same, it comes out to be 1. In case you care, there's actually 2 more definitions I can show you on how to do n choose k. I can also say that n choose k is equal to the value of pi as your index goes from 1 to k of n plus 1 minus I all over I, which is kind of crazy. This one you can run into problems computationally because you're dividing by a number. And division is always bad in computation because we can't express fractions perfectly. So that's something else we've got to worry about. Another crazy definition that we have, which is a recursive one, tells us that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And so it's like this recursive definition, and you keep going, and you stop when you either get to n choose 0 is the same thing as n choose n, which is 1. So those are 2 other definitions that you can use for binomials, for the n choose k kind of thing. One of the neat things also, random facts about binomials, which is apparently what this video is that if you've ever seen Pascal's triangle, so we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So the idea is you take this number and add it together to get a 3. So you always start with 1s on the outside. So you have 1, 1 plus 3 is 4. Why did I switch thicknesses there? So 1 plus 3 is 4, 3 and 3 is 6, So if you go through here like this, and then what do we have? 6, 15, 20, 15, 6 and 1. This is actually n choose k as well, it's just kind of cool. So this is all kind of related in that if you have like, let's say a plus b to the 0, you get 1. If you have a plus b to the 1, then you get 1a. So a plus b to the 1 gives you 1a plus 1b. If you have a plus b squared, that gives you 1a plus 2ab plus b squared. Yeah, does that make sense? Let's move this over so we can play. So this one gives you 1a squared plus 2ab plus b squared plus 1b squared. Again, a plus b cubed is 1a cubed plus ba squared b plus 3a squared b plus 3ab squared plus b cubed. I'll write that out, it's just easier. A cubed plus 3a squared b plus 3ab squared plus b cubed. And so basically if I wanted to come down here, I could do this. So this is 3, 4, 5, 6. So if I wanted to do a plus b to the 6th, it would be 1a to the 6th plus 6a 5b plus 15a 4b squared plus 20a cubed b cubed plus 15 a squared b to the 4th, and then I've got to move this over because this is really, really long and I'm running out of space. That's supposed to be a 4. It's kind of hard to see. B to the 4th, and then plus 6, a to the 1st, b to the 5th, plus b to the 6th. So I don't actually have to multiply all that stuff out. I can just memorize Pascal's triangle and just kind of go nuts. So that's kind of a neat little thing. Officially, that's called the binomial theorem. So we'll just go ahead and write that down for funsies. All right, so we've got the binomial theorem. And the binomial theorem basically says that if I have, I'll use a's and b's, a plus b to the n, that's given by the summation of k equals 0 to n of n choose k, and then a to the k, and then b to the n minus k. So each one of those terms would be, so each one of these summation terms is each one of 1, 2, 3, 4, 5, 6, 7, is each one of those terms. So that's where that summation is. This is basically saying like that. So another super kind of weird aside of this, come back. If we let a plus a equal b and, or sorry, a equal 1 and b equal 1, then what that gives us is 1 plus 1 to the n, also known as 2 to the n. So if I plug that in, I've got k going from 0 to n of n choose k of 1 to the k times 1 to the n minus k, and basically those ones go away, so I've got the sum of k going from 0 to n choose k. And what that means is that the sum of the rows of Pascal's triangle would give me the powers of 2. Okay, so basically if you sum the rows of Pascal's triangle, you get powers of 2. I can show you how to do that. So if we kind of go back up to our Pascal's triangle over here, if I look, the sum of the first row is 1, and then it's 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. And then the next one adds up to 16. And the next one adds up to 32. And the next one adds up to 64. So this is all kinds of crazy. So kind of being able to play a little bit with Pascal's triangle and binomials can let you do some pretty neat things. This is just kind of a brief introduction.